yesterday when we were going through this task, we talked about when you're adding the same amount every time, that gives you an arithmetic sequence. An arithmetic sequence has a common difference. Okay? And the reason they call it a common difference, even though we're adding the same amount every time, is because you can take any term and subtract the one before it. 6 minus 2, 10 minus 6, 14 minus 10, 18 minus 14. And you get that same common difference, which is the amount that you add to the previous term. Okay? So that is an arithmetic sequence. Now we talked about two formulas yesterday for arithmetic sequence. We talked about recursive, and I told you how that one's not very helpful at all. A recursive for an arithmetic has two parts. Part one is where we say the first term is, and whatever it is. So in this case, the first term is 2. And then what you do is you say, to get to any other term, you take the one before it and add the common difference. In this case, the common difference is 4. So in the first block goes the first term. In this block goes the common difference. That is the recursive formula. Now, recursive formula is helpful for some sequences, but not really at all for an arithmetic. The recursive formula is the only way we can explain some sequences. All right. The second formula we looked at was the helpful one, the explicit. And the explicit helps us find any term in the sequence. And this is that formula. And I think it was like number 6 was supposed to help you develop this formula. So you can find any term, not just the next one. You can find the 100th term or the 1000th term or any term you want in an arithmetic sequence using the explicit formula. All right, so that's kind of a review of the first little part. And those of you that want to write down these two formulas in one little spot to reference later, you sure can. Then all this was specific to this first problem. And we talked our way through this, and we developed this formula, and we talked about all the parts yesterday. This A sub 1 represents the first term. If you want to add that to the little notes we just did, that's fine. D represents that common difference. The common difference is the amount we add to a term to get to the next term. And N represents the number of the term, or the position in the sequence. Is it the first term, the second term, the third term, the 80th term? Where does that term lie in the sequence? So that's what N represents. A sub N is the actual term. So let's go over this terminology. If I gave you this sequence, 1, 4, 7, 10, ... Okay? What is A sub 1?
First term.
The first term. And in this sequence it is 1. Okay? What is the common difference? What is D? 3. Okay? Now, here's another question. What term is in the 4th position? Or what is the 4th term? I could ask it either way. 10. So A sub 4 is 10. The 4th term is 10. Okay? Okay. where would 40 lie? If 40 was the last term in this sequence, what is n? Where does it lie? What is its position in the sequence? How would we find that? We would plug in 40 equals 1 plus n minus 1 times d. And guys, you can put d at the end or you can put d at the beginning. Whichever way looks better to you. It's the same thing. Okay, and then we just solve this. So we'd subtract 1. We divide by 3. We'd add 1. So 40 is the 14th term. N is 14. It's the 14th term. Okay, so on the back of that first page, what we talked about is how this relates to a linear function. How does an arithmetic sequence relate to a linear function? If we graph it, it forms a straight line. Now, why do we not connect the dots?
Because there's no in between.
Because there's no in between. This is discrete. So, if we talked about this in terms of domain and range, our domain is our set of counting numbers, natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. First position, second position, third position, or you could say first term, second term, third term. That's our domain. So, we're not going to connect that because there is nothing in between. There is not a 1.5 term. All right? In this case, in this particular problem, our independent variable, that's generally our x, what lies on the horizontal axis, is the number of months, and the dependent variable, which is our y, our vertical axis, is the amount of money we saved, because the amount of money we save depends on the number of months. So if you can say it like that, then you can figure out the dependent versus the independent. Now, yesterday we did point out that that common difference does end up being the slope of this discrete data points that would form a line. up 4 over 1, up 4 over 1. Our common difference was 4. Did you guys just count by ones on this axis? Yeah. Okay, that's fine. All right, now, yesterday I talked about how the slope is the important part. We ought to be able to relate the slope to the common difference. The slope to the common difference. The slope is our common difference, either in explicit form, which is what 1 and 2 are, or in recursive form, which is what 3 and 4 are in. So the slope is the important part. The y-intercept is not as important to me, and the reason why being is in the sequence, the y-intercept doesn't exist. We didn't define anything as a 0 term. We started with the first term. And so because our independent variable can never be 0, we're not going to have a y-intercept. So I'm okay with us not solving for a y-intercept. Seems a little silly to me. All right, number 9. I like this first problem asks us to find the next few terms. Don't overthink that. Just continue the pattern. If this is plus 3, plus 3, plus 3, plus 3, keep adding 3. Done. All right, now, if the last term in the sequence is 133, how many terms are in this list? This is like the one I just did a minute ago. We are solving for n. They're giving us the last one. That's our a sub n. We plug that in, and we are solving for n. So you should have gotten 45. Now, the next section was a review of quadratic. We're not doing quadratic right now, but they threw it in there. If we look at this list, the first difference is not constant. If we look at it, the first difference is not constant. This is 3. This is 5. This is 7. But the second difference is constant. This is 2. This is 2. When I subtract 5 minus 3, I get 2. 7 minus 5, I get 2. Maybe you remember from studying quadratics in 9th grade. Probably not, but maybe. And this is kind of important. It could pop up on the SAT. I don't think on the ACT. But if you notice that the second difference is constant, then it's a quadratic. Now, some of you may have just looked at them and went, ooh. Yes. I don't know what that means. Should I use both?
Use both.
Both?
Ask Jack Blum.
I know.
I say use both.
It'll pop up again, just exit out for now.
Yeah.
Okay.
Tell me again.
You can't exit.
Uh-oh.
Oh, I gotta make a choice.
Click don't tell me.
Raise your hand for
Anybody got a
yes.
coin?
Click that.
Yeah.
But then,
Don't.
alright, I'm using both. Alright. If you guys haven't noticed, when you open up your email, it's going to tell you Google Drive is going away. And so that's why I had to download
Wait, Google Drive.
Google File Stream.
What's why they
Okay,
Google Drive?
so it's a Google choice. They probably came up with something that takes up less space and is quicker.
So we're not gonna go to Google
So-
Drive anymore.
I think what's going to happen is just like I did, you're going to have to migrate all your information into Google File Stream just like I did. Alright, maybe the county will do that for you, I don't know. But anyway, if you notice, if I square this and add 1, square 2 and add 1, square 3 and add 1, square 4 and add 1, that's the explicit formula. I didn't expect anybody to get this one right. Did anybody get it right? No? Okay. I had 3 people in 7th period get it yesterday. I gave them all a Smartie.
I got it right.
That was a Smartie. Okay, so once again, if we notice that second difference is constant, it's a quadratic, and that's really just review. You don't have to know that now. Okay, now, this was our exponential. So this is what you had to do on your own yesterday. We kind of walked through the arithmetic. Exponential gives us a geometric sequence. It's geometric when you are multiplying by the same amount. And that same amount is called a common ratio. Alright, so what does this formula look like? This is what you were supposed to come up with. Oh, not a capital G, lowercase g. Those have different meanings. G sub n is equal to G sub 1. R, your common ratio to the n minus 1. So if we're multiplying by the same thing every time, this is our formula. So G sub 1 represents the first term, R represents the common ratio, n represents the number of terms. This is our explicit formula. This is, once again, the most helpful formula. The recursive formula has 2 parts again. First part, first term is blah. Okay? To get to the next term, you take the term before it and you multiply by the common ratio. Alright, so specific to this problem, the recursive formula would look like this. The first term is, what was it? 0.25. The common ratio, what am I multiplying by? 2, 2, 2, 2, 2. It is 2. Oh, this is not recursive. This is explicit. Sorry. Hold on. Yoop. And to get to any other term, we take the term before it and we multiply by 2. That's recursive. Explicit would look like what I was doing. G sub n equals the first term times the common ratio to the n minus 1. All right, so when we're multiplying, it's geometric, and these are our formulas. Okay. So this is what we just talked about. If you already wrote it down, you don't need to write it down again. We did that. We did that. Okay, so once again, recursive is quite limited. It just gives you the next term. If we wanted to know 4 years later, which would be 48 months, we would not want to do the recursive formula 48 times. So that's where we want the explicit formula. Okay, and once again, when we compare these two, we see they're 1 less than. That's why we get that n minus 1 again. But this time the n minus 1 is the exponent, because it's an exponent here represents that repeated multiplication. So that leads us to the explicit formula, and somehow your box jumped to the top of the next page and covered up important stuff. Sorry. All right. Okay. Now, this is bad. This key has the dots connected. Should they be connected?
No.
No. See if I can wipe that out. Go away, line. It should just be those beautiful pink dots. All right. All right. Now, with the line in there, you actually can see the exponential function. An exponential function, its graph does increase like this if it's exponential growth, which this one is. So that's the reason they drew that line in there, so you could actually see the exponential growth. But those dots should not be connected because, once again, this is discrete data. Now, with these, can you pick out r and g sub 1? We don't have a constant slope here because it's not linear, so we're not going to ask you for the slope. We could find a rate of change, but we can't find the slope. All right, now this one's cool because r, look at it, negative, positive, negative, positive. To make it change signs like that, my multiplier is negative. So whenever they change signs, that r, that common ratio, what you're multiplying by, is negative. So it just flip-flops signs. Yes, sir?
How did you get 2/3?
How did I get 2/3 for which one?
For G1. G sub 1. On number 2.
All right, instead of giving this formula to us in n minus 1, they gave it to us in n. That was just kind of mean. So you had to go back 1. If I give you one like this, it'll look like this one. It'll be in the right form,
Can you do this?
where you can see the first term and you can see the multiplier. This was really tricky to be the first one they asked you.
No, I mean, can you do like the thought process?
Yeah, instead, because 3 is not your first term, it's actually your second term. Because this is not n minus 1, it's just n. That 3 is your second term. So you had to go backwards to find the first one. So to go backwards to find the first one, you would take this and instead of multiply by the common ratio, you would divide by it. Actually, this is your 0 term. You had to multiply by it to find the first term. That's your 0 term. This is not a good form. This was bad form. Sorry. This is what's important. All right. Okay, so this is the correct form, n minus 1. So when we have the correct form, then we know our first term is 2, and then we multiply by a fourth. So 2 times a fourth is 2/4, which is 1/2, times a fourth times a fourth times a fourth. All right, now if it's a decimal number, I want you guys to change it to a fraction whenever possible. Do you know how to do that on your calculator? You hit the math button, and then fraction, woo, and then enter. Math, fraction, enter. Because otherwise it's a really ugly, crazy decimal number. All right, now the last question asks you to compare the two. Gina's situation was geometric. So this is Gina, geometric. Ashley's situation was at part 1, Noah. And so that's arithmetic. So for $10,000, we would plug 10,000 in here and solve. So to solve this, you can either take the log or the natural log of both sides here. Either way, log or natural log to solve. And that's what we just finished in our last unit. That is the reason why this little section follows logarithms. So for Gina to get to $10,000, it would only take her 16.288 months. So by the 17th month, she would have 10,000. Now Ashley was a linear situation, an arithmetic, and it would take her 2,500 months. Gina's in a much better situation. Okay, so important parts, arithmetic, adding. Use this formula. Geometric, multiplying. Use this formula. Okay? So what we have today is a lot of practice, and you have the rest of class to practice. Okay? So you're practicing using arithmetic, practicing using geometric. All right, if you didn't pick up the worksheet on your way in, it is on the bookshelf. And let's go ahead and give that a try.